Our speaker this evening has formerly worked at Red Hat and is the founder of the Linux KVM Virtualization Infrastructure project. Please welcome the CTO of ScyllaDB, Avi Kivity.
Thanks a lot. So it was my lifelong dream to perform off-Broadway, and here I am. Thanks a lot for this chat. So you've heard about me. I'd like to get a little feel for the audience. How many of you are familiar with NoSQL, using NoSQL? Can you see some hands? Wow, everybody almost. How many are DBAs? Very good number. How many are DevOps, application developers? Okay, nice number. How many are here for the show that's actually for tomorrow and are here by mistake and have no idea what's going on? Oh, about 25. Bigger number. All right, so I'll talk about Scylla. If you're Greek, you're allowed to pronounce it as Scylla, but otherwise it's Scylla. So let's start. What's Scylla? It's a new NoSQL database. You can do 1 million operations per second per node, if you have a nice node. With that performance, you get really low latencies, which are also predictable, so low jitter. And it's completely compatible with Apache Cassandra, which I forgot to ask, but I guess a lot of you are familiar with. So to whet your appetite, here is a throughput comparison, comparing a 3-node Cassandra cluster in red, a 9-node Cassandra cluster in gray, a 15-node Cassandra cluster in yellow, with just 3 Scylla nodes running the same benchmarks. This is the YCSB benchmark, and on the x-axis we have the command load that the loaders were asked to push at the database, at the cluster, and on the y-axis we have the actual operations per second that were achieved by the cluster, and you can see that Scylla, the 3-node Scylla cluster, easily beats with some wide margin the 15-node Cassandra cluster, about 550,000 for Scylla compared to around 440,000 for Cassandra, cluster that's 5 times larger. All right, so first we'll introduce NoSQL. I guess since everyone's familiar, we'll go through it quickly. Talk a bit about Cassandra, introduce Scylla, talk about how it is compatible, what compatibility means in this context, describe how it works, how we achieve this incredible performance, give some indications about the roadmap, and close. All right, so introduction. So NoSQL basically is a different new approach to database, which trade-offs some SQL features for performance, for the ability to scale horizontally. So if you need more performance, you don't need to shell out for really powerful hardware or more bucks for Oracle, but you can just add more nodes. And you get, into the bargain, high availability and fault tolerance. What are you losing by moving to NoSQL? Firstly, you lose join. That's the cost of horizontal scalability. And the second thing you lose is the full ACID. You may get some parts of ACID, atomicity, but you lose isolation. You lose, it depends on the database. Different databases have different trade-offs. So common NoSQL databases, MongoDB, I guess many people are familiar with it. A document store, which means that it doesn't have a schema. You basically push anything you like into it, and then you can query. Not having a schema can be seen as an advantage because it's easier to start, but it can be a disadvantage later when your data gets all messy. Cassandra is another popular choice. It's a wide row store, and it has a schema. So you design the way your data is supposed to look, and the database validates that it indeed looks the way you designed it. And the third example is Redis, which is a simple key value store. So it's a real simple database. It's in memory. The persistence is not perfect. So it's not completely a database. It's more of a cache, but still it's a useful comparison. It's also a schemaless. Okay, let's talk a little bit about Cassandra. So Cassandra was introduced about a decade ago by people at Facebook. It's based also on Bigtable from Google and the DynamoDB paper from Amazon Web Services. It's written in Java, and we'll touch about that in the future. It has configurable replication, so you can select if you need 1 replica, 3 replicas, 2 replicas of your data, depending on your requirements. It has a symmetric architecture, which is one of the things we really like about it. It means there's no master and slave role for the nodes, and that simplifies it for administration. It reduces bottlenecks. It reduces a lot of headaches. It supports geographical distribution, so you can have a data center in different continents or in different places in different continents. So you can have a disaster recovery, and also you can choose the data center that is closest to you in order to get the best latency. So you can be writing in LA and reading in New York, and your reads will be fast if you're located close to the data. It has tunable consistency levels, so per query you can choose whether you want high consistency, meaning that you read exactly what you've written before, or you can trade off some of that consistency but get faster responses and better availability by choosing a lower consistency level. So that's a nice feature, and it's very useful if you have high availability or latency requirements. It's very widely deployed, so there are 1,000 node clusters around, and lots of people, lots of companies are running dozens of clusters. We think that 1,000 node clusters are a bit too much. I think that 100 node clusters are more like it. And some prominent users include Netflix and Apple. And this is not working. Dor, maybe you can help me with. Oh, it worked out. All right, thanks. Some features about Cassandra. It's both distributed and decentralized, so you can run it on as many machines as you like. When you're running out of capacity, either performance or disk, you can just add more nodes, and it's very easy to scale, and you don't need to mess with sharding. It does that automatically. So it's column-oriented. You have a set of rows which are addressed by a primary key, and the rows themselves are divided into smaller rows which are addressed by a clustering key and are also ordered. And this way you can have some organization to your data. So a partition may be correspond to a user, and say the internal rows may correspond to the user's page likes, or I don't know, playlist tracks. So you can organize your data. Unlike key value stores, you have some organization. So the way Cassandra and Scylla, because we work in the same way, is a log-structured merge tree. So what happens when you write is that you're writing to a buffer in memory, and when that buffer fills up, Cassandra will write a file called an SS table, which is a sorted string table. It's sorted, so lookups are very fast, and it deposits that file on your disk, and it moves on to writing the next file. And as time goes by, your disk fills up with lots of small files, and that results in slower read performance, because now for every read, you have to access all those 3 files, because your data may be on one or all of them. So what a log-structured merge tree does is, in parallel with writing the 4th SS table, it also begins a process called compaction, where it takes the 3 existing SS tables and it compacts them into a single larger SS table. In that process, it can do things like merge data, expire data that has TTLs, time to live marks, and reorganize the data for faster access. And in parallel, it continues writing new SS tables. And something to note about, and then when compaction is complete, it can delete the original files. So it takes a number of smaller files and it converts them to a larger file in this compaction process. And what's important to note is that the process of writing SS table, this is a foreground job because it comes directly from your data that you're writing. So application directly controls. But the process of compaction is a background job. It happens while your application is running, but is not directly initiated by it. And we will see later how this distinction between foreground and background jobs is something that causes a lot of headaches for Cassandra administrators, and this is something that Scylla solves. So it's not just adding performance, but also making administration easier. Some problems with Cassandra. So Cassandra cannot utilize the multi-core machines. So typically now you have machines that have a dozen cores or even 24 cores. They're becoming pretty common. And when you run Cassandra on such machines, you often see that even though you're pushing it as hard as it can, it will not utilize more than 70% of the CPU. It will just leave the CPU idle. There are cores available, but they cannot be utilized because the architecture is not built to address such large multi-core system. This is common with many applications. It's not easy to write well-threaded, highly threaded applications. You have high latency due to Java and the JVM. Sometimes the JVM decides to collect dead objects from the heap, so it does a garbage collection process, and that can pause your application, Cassandra, for up to a second, where it doesn't respond to network requests, it doesn't respond to your queries, and everything slows down. And because it's a clustered application, lots of requests from other nodes are also blocked, and basically it impacts your latency severely, especially in the high percentiles. Cassandra requires a lot of tuning and configuration. So I mentioned before the foreground and background jobs. So you have to configure the number of threads for the different types of background jobs. You need to configure the bandwidth for compaction and bandwidth for other jobs. And it's well known that people spend a lot of time, months, tuning both Cassandra and the JVM to get the GC under control. People hire consultants to do that because it's somewhat of a black art. And another problem is that maintenance operations, like repair is a process that is used to reconcile differences between nodes, and adding new nodes or decommissioning nodes that you want to put under maintenance, they impact performance a lot. So people are either not doing them or trying to find a point that they don't need all of the performance, like in the weekends, and that causes a lot of headaches. All right, enough about Cassandra. Let's talk a little bit about Scylla. So in just one, in a nutshell, Scylla gives you the power of Cassandra, all of the data modeling, the geographical distribution, high availability, tunable consistency level, but at the speed of Redis, which is basically an in-memory database. So it gives you the best of both worlds. So it works in the same way that we really like the overall architecture of Cassandra. We just have issues with the implementation. And it gives you the same multi-DC support. You have the same access to the ecosystem. So if you're used to running Spark against Cassandra, you can run it against Scylla. It supports the same SQL query language. When you're adding a node, it will redistribute the data automatically in the same way. So it's the same feature set, just faster performance and automatic administration. Here are some more performance benchmarks. This is a 30-node Cassandra cluster against a 3-node Scylla cluster. It's the same YCSP benchmark I showed before. And you can see that Cassandra with 27-node advantage is performing somewhat better than Scylla. But if you look at latencies, here is the average latency. This is a mixed read-write request, 50% reads and 50% write, and we're looking here at the y-axis on the average latency in microseconds, and you can see that the Cassandra 3-node, 5-node, and 15-node latencies are way higher, even at lower throughput, than Scylla with just 3 nodes. So if your application is latency sensitive, and this time a lot of applications in the ad tech space or similar are very sensitive, or e-commerce, where if the user doesn't see the page in time, they're just going away to your competitor. then Scylla can help you here. If you're looking not just at the average latency, but at the 99th percentile latency, the difference becomes even more marked. So here we can see that 99th percentile latencies for Cassandra can be in the area of 25 milliseconds, while Scylla at a much smaller cluster, 5 times smaller cluster, and a much higher load, it gives you just 6 milliseconds at 99th percentile. And this is the average latency for a 30-node Cassandra cluster compared to a 3-node Scylla cluster. All right, I explained before about how Cassandra administration is pretty difficult. You need to tune many things. You need to configure the bandwidth for the various internal processes. But Scylla is not like that. Scylla self-tunes. So Scylla is aware of all of the hardware, and it divides dynamically the available bandwidth, disk bandwidth, network bandwidth, and CPU bandwidth among the processes, the internal processes. These include the front-end processes for serving reads and write, and the background processes for doing compaction, for doing repair, and for streaming, which is moving data to new nodes in order to provision them. So we try to utilize the hardware as efficiently as possible, and that is why we wrote it in C++ in a native language and not in a managed language. We make sure that there is good observability of everything that is going on. So we expose dozens of counters which tell you about what's going on inside the server, so you can understand what's going on. The maintenance is a lot easier. So you don't need to worry when you are provisioning a new node that the impact from streaming will bring down your read and write performance, or will impact your latency. They will remain the same. But the tooling is compatible. So if you have some kind of process around administering Cassandra, like you're using JMX or you're using a node tool, then those processes can continue to work in the same way. Even the backup and restore are similar. This is an example of our monitoring dashboard. So you have here, you can see the internal load in the server, the request per second, various errors. And we have this as a Docker image that you can just pull and use to monitor Scylla. So what can you do with 1 million operations per second per node? So the obvious thing is to shrink your cluster. And if you're running hundreds of nodes or thousands of nodes, then it's pretty obvious that the savings can be enormous. And it's not just the savings in capital expenses or operations. It's also in headaches. When you have 1,000 nodes with, say, a 3-year MTBF, then you're basically having a failure every day. Every day you're parting in a new node and moving in a burned out old node. So by shrinking your cluster, you're both saving money and saving a lot of work for maintaining that cluster. You can handle spikes. So if you have a very varying workload with spikes, then you can have the extra capacity to withstand those spikes. We've seen that a lot of Cassandra users use Cassandra as a key value store instead of modeling it as a schema with individual columns. And that is they don't do that by choice. They do it because they are forced to. Using the Cassandra correctly with columns is too slow, so they're just serializing everything into a big JSON string and sending that into the database. That means that if they need to modify one field, they need to do a big read, modify, write. And it's also harder to ensure that the data is consistent later on. So with Scylla, because you have the extra performance, you don't need to do those tricks. You don't need to change your application. You can just push your data to the database as is, and it will handle it. You can run more queries against your data. So we've seen that people are trying to save on the number of queries, trying to optimize the number of queries they send, just because the database is not able to handle it. With Scylla, you don't have to worry. You need more queries to improve your business algorithm. Send those queries, and Scylla will serve them. You can do maintenance operations while running you then need to worry about the impact on latency and throughput. And you can stop putting caches. That's also something that we see a lot. People are putting memcached or Redis in front of the database, or sometimes a cache inside the application. And then you need to manage those caches. You need to invalidate the caches in order to not get stale data, and that's a lot of headaches. With Scylla, you can let the database cache the data for you, send the query, and return you coherent data. And you can stop worrying about latency. So a lot of people running Cassandra have big latency problems, often from garbage collection, but also from other issues. And with Scylla, you will get consistent and low latency. All right, let's talk a little bit about compatibility. I mentioned that we're compatible with Cassandra. Let's see what that means. So in a nutshell, it means that it works exactly the same way. So the same SS tables that Cassandra uses, we read and write the same format. You can go back and forth with those files. The same SQL language that you use to write your application can be used with Scylla. So it's the same language, the same syntax, and also the same binary protocol that the drivers use to communicate with Cassandra is the same protocol implemented by Scylla. So that means that your drivers do not change. If you're using the DataStax Java driver or the Go SQL driver to talk from the Go language to Cassandra, then it will work with Scylla as well with no change. And that means that your application basically does not need to change. On the operation side, it's a similar story. So the protocol that Cassandra uses to manage is JMX, the Java Management Extensions protocol. And there is a command line tool called NoTool. And we support the same protocols. Even though Scylla is not written in Java, we support the JMX protocol. And we support the same NoTool with the same syntax. So if you have scripts that they call NoTool or whatever, or if you're just used to it and want to keep using it, then you can. There's no changes to your procedures. All right, and everything I just said is repeated here. There are a lot of advantages to being compatible. So it's not just that your application can be migrated easily. It's also the ecosystem that supports Cassandra also supports Scylla. So Spark and Presto are two very useful analytic engines that can be used with Cassandra, and that can also be used with Scylla, and they gain from them improved performance, and we've tested them, and there are plenty more participants in that ecosystem. Everything that works with Cassandra will work with Scylla, only faster. So if you have an application running Cassandra, you must be wondering how do you do a migration from Cassandra to Scylla. There are two answers to that question. So the first answer is a simpler one. It's just stop, install, restart. You take a cluster, you shut it down, you install the Scylla, you provide the RPMs or depths, and you start them. And the configuration file is the same. So Scylla will start, and it will serve your data. But of course, the downside of this method is that it incurs downtime. So we have a different method that we support, which is a double cluster, where you set up a cluster in parallel. That method incurs no downtime, but is more complex and needs some more hardware. We have a tool called SQL Proxy that you can install. And what SQL Proxy does is basically split the SQL stream, splits the query stream into two. One half goes into Cassandra, so all of your writes are replicated, and the reads are also sent to both clusters, and you can compare them to be sure that the data is the same. And once you're satisfied that everything is working correctly, you can just flip the switch, and Scylla becomes the master cluster, and Cassandra becomes the secondary. And once you're happy, you can just shut down the Cassandra cluster, and your migration is complete. And you can do that. You can run them side by side for as long as you like, until you're satisfied that everything is working correctly. All right, let's talk about how the magic works, how we do that. So when we started Scylla, we observed that modern disks are really network devices. So when the little connector on the left is really a network port. When you're issuing a read command to the disk, you're actually sending it a message that says, initiate a read of this block, of this vector. And the disk goes off and does the read. And your application needs to go and do something else. But that's not how applications are written today. Usually they just wait until the read comes back. And then when the data is available, the disk sends it on the connector, sends it through the SATA wire, and it becomes available on the host CPU, and then your application is resumed after blocking. But that's not the right style of writing network applications. The correct style is to work without blocking, to send a request and then keep on doing something else from your keep on processing, and when the response becomes available, then you pick it up and continue processing, instead of suspending your threads and incurring a context switch each time. But that's not how applications are written. Another thing is that if you look at the modern processor, and this is a modern Intel Xeon with 22 cores or something like that, it's actually also a network device. So those red rings around here are two internal networks that are used to connect the cores. The cores are on the outside here. And those two internal networks are connected by internal switches. And if you have two sockets on your system, then those two sockets are communicating via the QPI ports. So there is a lot of networking inside a CPU. A CPU is really a set of network devices, dozens of network devices connected via an internal fabric. But applications are not written to take advantage of it. The way applications are written, when you need to access a bit of data, you take a lock and you access the data. And while you're holding the lock, all of the other cores that need to access the same data are blocked. They have to stop. So instead of working in a non-blocking way, like you expect network applications, they have to stop and wait until the data comes, or you can context switch, which is in itself expensive. So when we observed these two issues, we decided to start the C-Star project. So C-Star treats storage and multi-core in the same way that most applications treat networking, in a non-blocking way. So we're using a thread per core design, and everything works via message passing. It's using futures and promises, which is a neat API. It's also available in other languages. And also, it includes a user mode TCP/IP stack, which speeds up communications even more. If you want to know more about C-Star, then you can set your time machine to 1 month in the past, and you can attend the C-Star meetup that I did here in New York City in May. So see you then. All right. Let's talk about the internals of Scylla. So this is very related to C-Star. We're using a shard per core. So in the same way that Cassandra shards the data, so every node holds a portion of the data and uses a hash to address that data, and the data is spread across the cluster. Scylla treats, this is also true for Scylla, but in a different level, we also do it inside the node. So each core in the system owns a particular portion of the data that belongs to that node. And instead of accessing that via a shared structure with a lock, when one core needs to access data that is on another core, it sends it a message on an internal point-to-point queue, asking to do the processing for the data, and gets the response back on a return queue. We also have our own cache, and we have some slides explaining about the cache, not using the Linux page cache. Our storage engine is schema aware, which means that it knows the layout of the data and it takes advantage of that. And we generally work to maximize the hardware resources. So we take, if you have 128 gigs of memory, then Scylla will allocate about 120 of those, and it will use all of the memory for caching. So it doesn't leave memory for the operating system, because the operating system is not aware of how the database is tuned. It doesn't know which data the database will need, so it cannot manage the cache effectively. Instead, Scylla takes over all of the memory on the machine and uses the memory in the best way. And we have our own I/O scheduler, and I will explain later what that means and why it's important. So this is this slide explains the differences between Cassandra and Scylla. On the left, you see the Cassandra architecture, but it's really most applications are written this way. It's not unique to Cassandra. So you have a bunch of threads, and those threads are multiplexed by the scheduler on a smaller number of cores. So you might have hundreds of threads running on top of dozens of cores. And why do you need so many threads? It's because of the blocking problem that I related to earlier. If you have a small number of threads, then you can't take advantage of all of the cores. And when one of the threads accesses data on storage and it needs to block because the APIs are designed for blocking, then you need another thread to jump in and take its place on the core. And that causes a huge amount of problems. If you have many threads, then the kernel needs to make a decision between those many threads. It cannot always make the best choice, and always computing the next thread to run and doing the context switch, it's very expensive. You probably all know that context switches are bad. So you might want to reduce the number of threads, but then you might find your machine is idle because it cannot find enough threads to run on all of those 20 cores that you have. The same thing happens with memory. So you have a bunch of memory on the machine and a bunch of threads, and you need to divide that memory between those threads, and the kernel cannot make the right choice. It doesn't know how it's supposed to work. So let's look at the C* stack in comparison. So that's the C* framework that I described earlier. So what it does is it runs a stack that is replicated across each core. The stacks are completely independent. Each core has its own task scheduler that is responsible for managing the task that's running on the node. A task in this context is something really small, so it takes about a microsecond to run. Each core is capable of running maybe 500,000 tasks per second, and a task is responsible for initiating an I/O operation or completing an I/O operation that was initiated by a previous task. So it's basically churning through those tasks, and when one core needs to access data that belongs to a different core, instead of accessing it directly and trying to coordinate everything with locking, it sends it a message that says, please perform this operation for me on that remote core. It places it on a queue, just like it would when communicating with a different network node, and continues on. And we can also use our own TCP/IP stack, but I'll skip over that. All right, let's expand a little bit on tasks. So usually when you're having a threaded architecture, then a thread keeps the context on a stack. So you have those large stacks, and every time you switch to a thread, then you need to, your cache, not your application cache, but the CPU cache becomes less relevant. So it needs to be flushed out, and then the cache for the new thread needs to be loaded, and the context switch cost can kill the application. It's tens of microseconds or even more in some applications. In Scylla, you just have a bunch of tasks that are each are a few dozen bytes, and this way the cost of switching between them are really low. They're nanoseconds. So we can do millions of tasks per second per core. All right, let's talk about the cache. So looking at Cassandra, there are several different types of caches. There's the key cache, and there is the row cache. Either of these can be tuned to be on heap or off heap, so inside the JVM or outside the JVM memory. And you also need to use the Linux page cache. You need to keep most of the memory for the Linux page cache. And that brings the first problem to mind. You need to configure all of that, and you need to tune it. So, and the tuning takes time. It takes a lot of effort. You need to benchmark to decide what the right values are. And those values might change. Your workload changes with time. Your queries change. Your usage change. So what's a correct tuning for one load might change later on, and you need to retune it and it's a huge headache when it's a live application that cannot be brought down. In Scylla, we have a unified cache, and it doesn't have any configuration parameters. So actually, we accept all of the configuration parameters from Cassandra, but we ignore them because we just accept them for compatibility, but we ignore them because an admin shouldn't have to configure all of the things. The database should be able to divide the resources that it has internally according to the workload. A different problem is parasitic rows, and that's a problem that's specific to the Linux page cache, which is where most of the memory in Cassandra is used. So what are parasitic rows? Imagine that you have a data object that is 300 bytes in size, and you're reading it from disk. So what happens is that Linux will allocate a 4K page, and we read the contents of that page from disk, because that is a basic unit of cache management in Linux. And if your data is just 300 bytes, then you have about 10 times that size that is just unused. So you're utilizing about 10% of your memory to store those 300 bytes. And of course, that will impact your caching. You will need to go a lot more to disk. And of course, your latencies will go up and your throughput will go down. You're transitioning from memory throughput and latencies to disk throughput and latencies. In Scylla, we always store objects, so you don't have this problem of parasitic rows. Another problem is page faults. So the way that Cassandra uses a page cache is by mapping the memory into its address space. So it looks pretty simple. You map the data, and then you just access it using normal memory operations. And if the data happens to be in the cache, then all is great. You get memory access speed, just a single instruction to read memory, and it's incredibly fast. But if the data happens not to be in memory, then you get this little scenario. So what happens is that the application thread has to take a page fault, which by itself is about a microsecond or two. And if you're doing 1 million operations per second, then that's a lot of time. The kernel then has to initiate a new I/O to fill that page from disk and do a context switch and find some other thread to run. So you're not paying for a context switch. Now the SSD receives the request and does its thing, fetches the data, DMAs the data back to the kernel, and now the kernel has to perform the map, link the page into the application memory, and switch context back into the application and resume the thread. So you're doing a lot of work every time you miss on the cache. In Scylla, that doesn't happen because the cache is completely in the application memory, completely in the application context, and not managed by the kernel. We know ahead of time whether the data is in the cache or not. If it's in the cache, we access it and return the result. If it's not, we initiate an asynchronous operation, an asynchronous DMA operation, which will DMA the data into Scylla memory and inform us when it's complete. So we don't need to take all this side trip into the kernel and back and do all of those context switches. All right, we also have an I/O scheduler, which I mentioned before, and I'll explain what it is and why it's so crucial for Scylla performance and tuning. So it turns out that every disk has an internal concurrency, a maximum concurrency setting under which it performs well. And on the left, you can see a graph that's a nice, very fast NVMe disk that we have. And you can see on the x-axis is the concurrency, the amount of operations that are running concurrently on the disk. Those are 4K read operations. And on the y-axis is the throughput in operations per second. So you can see that up to about a concurrency of 140, you push more requests and the bandwidth increases. It's able to take those requests and serve them in parallel. But after that area, highlighted in purple, you're pushing more requests to the disk, but it's not able to take advantage of them. It's just queuing them. So instead of the bandwidth increasing in blue, you can see the bandwidth plateaus. You can see that the latency starts increasing instead. The bandwidth stays the same, but latency increases. And instead of enjoying more bandwidth, you're just suffering for increased latency. So what the first thing that Scylla does upon installation is run a benchmark, and it does it internally. You don't really see it. You're just waiting for about a minute until the benchmark completes, and it identifies this sweet spot of concurrency for the disk. So it tunes itself to your disk capabilities, and it records its information. So let's look at what happens in a traditional stack like Cassandra or many other databases, and what happens in Scylla. So in a traditional stack, you have lots of internal processes. So there's light blue circles that are all talking to the file system and the kernel, and eventually reaching the disk array. So if you have, say, 1,000 operations, and they're all getting queued, if you have a fast disk, then 150 of them are being served by the disk, but you have 850 that are waiting in a queue somewhere in the kernel, in the file system, in the block layer. It's really hard to find out where. And if you have yet another operation coming in, it will just get queued at the tail end. So the 1001th operation will get queued at the end. In Scylla, what we do is, instead of just throwing everything as a kernel into the file system, we only allow up to 150 operations, or as many as your disk likes. We only allow up to 150 operations to be processed by the disk. Everything else is queued over here in user space, in Scylla itself. And if you have all of the 850 other operations will be queued above that in this layer. And that means that if you have, say, 850 write requests that are queued for write, and you have a read request coming in, then that read request can bypass all of those queued requests and go directly to the kernel, because it doesn't have to wait for anything. It has to wait until at least one operation completes, but it doesn't incur the extra latency. So this way we can dynamically prioritize and control the latency of various requests. And that allows us to have reads and writes that are happening in parallel, and yet the reads do not overwhelm the writes, or vice versa. It allows you to start to commission a new node and start streaming data from all of the nodes, but without impacting your regular operation, without impacting latency. It allows you to run repairs, and all of that without worrying and without configuring your repair throughput. So to give an example, in Cassandra, you have to configure the speed at which compaction runs. You tell it, please compact at 25 megabytes per second. And it's really hard to get it right. If you set it too low, then compaction will fall behind, and you will have a lot of small SS tables, and then your read performance will suffer, because each read has to access all of those small SS tables where your data might be. If you're setting compaction too high, then you will have a small number of SS tables, but your write throughput will suffer because because Cassandra is doing compaction instead of doing your writes. In Scylla, you do not have a setting for the compaction bandwidth. It adjusts it dynamically, and it can do it because it knows what your disk can do, and it can queue those operations separately. So each operation has the identity, its IO priority class still attached from the point it is born until the point it completes. These are examples of our IO scheduler. So that's not taken from Scylla, that's taken from a blog that explains exactly how it works. So on the left, you have the shares distribution. So you have several different distributions, equal shares and different shares. And on the right, you have the resulting throughput. And you can see that by adjusting the different shares, you get different throughput for the different classes. It's similar to setting the priority for a CPU scheduler, except that it's for I/O. And this is an example of how you can do a repair, which is a maintenance operation, in parallel with regular serving, and the impact is minimized. So you can continue serving while running maintenance operations. All right, let's talk about the roadmap. So let's look at the road we've already taken. So we went GA a couple of months ago, and with 1.0. In 1.1, we added the outer table, user-defined types, authentication, encryption, and an SSable loader tool. And right now we're releasing 1.2 with the outer key space and a few other smaller modifications. So you can see we're running pretty quickly. In the near term, we're adding day-tiered compaction strategy. So the compaction strategy tells you which SSable to pick for compaction. There's more than one way to do it, and this is one we're missing. We're adding a CQL tracing, which allows you to tell Scylla to trace the request and tell you exactly what steps it took to fulfill it, and you can understand what's going on. And we're improving performance for write rows. Those are rows that can be larger than your memory. And in 1.4, we're adding Rift support, which is another protocol. It's actually an older protocol that can be used to access Cassandra. And there are lots of applications that are willing to support Rift, and people don't really want to port them to the newer protocol. So we're humoring them and adding this protocol. And secondary indexes, which allows you another way to find your data. For the midterm, we're adding a management console, a GUI that you can use to perform operations and monitor Scylla. A REST API, so we actually already have a REST API, but it's not labeled production ready. It's used internally between our JMX process and Scylla. Materialized views and continuous repair, which reduce the windows in which your data might be inconsistent. And for the longer term, those are more interesting projects. So the first is the in-database analytics. So currently, if you want to do analytics, like doing full row scans and get some insight about your data, you have to use external tools like Presto or Spark. And while they're good and they work really well, you need an extra cluster for them, and you need to administer those clusters. And so we're going to offer a way to do analytics inside Scylla to utilize the power of the database. So you can do the analytics directly. And again, we will use the same techniques that I showed earlier so that your analytics do not impact your real-time processing. So you can continue to serve while doing your analytics. Another feature which we're really excited about is multi-tenancy. We've seen that many Cassandra users have dozens of clusters, sometimes really small clusters, sometimes very large clusters. And they do that because they are afraid of having different applications running on the same cluster impacting one another. There is no real SLA, service level agreement guarantees in Cassandra. What we're going to do is to extend the same isolation features that I've shown. In the same way that we isolate reads from writes and reads and writes from maintenance processes, from background processes, we're going to use them to isolate different tenants from each other. So you'll be able to have one large cluster, as much as your company needs, and you will be able to divide it into virtual clusters, and the administrator will be able to specify an SLA. So you will be able to say, this tenant is allowed to use up to 10% of the storage and up to 5% of the CPU power and up to 5% of the networking bandwidth, and Scylla will only allow it that amount. If there's more, then you might allow it to use more. But it will cap it, if there is contention, it will cap it at that amount, and you will be able to be sure that you don't have impact from one application on another. And the savings here can be enormous. Setting up a cluster, and the minimal cluster is 3 nodes if you want replication. It can be 9 nodes if you need a geographical distribution. All of the administration overhead, managing upgrades and the backup and restore, all of that can be consolidated into one cluster in the same way that the VMware and virtualization allowed you to consolidate many applications to run on one physical host or a small number of physical hosts. This will allow you to consolidate many databases onto just one or maybe a few, and still maintain SLAs. And the third feature is storage plus memory. So you might have heard about Intel and Micron announcing memory that is in between flash and RAM. So it's faster than flash and cheaper than RAM. So So you will be able to easily have a server with a terabyte or 2 terabytes of memory. And you've seen that our caching algorithms are very powerful, and they are really ready to take advantage of these massive amounts of RAM, of memory. And you can have an in-memory load that is very efficient with the Scylla. All right. So what can you do after this? So you can, of course, run and download on our download page. You can follow us on Twitter to learn about different events that happen. You can download the source. It's open source, of course, on GitHub. You can subscribe to the mailing list to ask questions. And you can look at the company site and the blog. We have a really good blog, if I say so myself, with a lot of details about how we test Scylla. We have a very extensive test suite about the internals. So you can read about the I/O scheduler. You can read about how we tune, we minimize latency. Lots of interesting things in our blog. And that's it.
Before we go to the Q&A, as I said initially, we're doing a raffle at the end for an iPad mini. If you still want to join us, bring us your business card and we'll put you into that raffle as well.
Keep someone pass around the business card.
If you can do that, that's your job.
Guys, just pass it around. And while we're collecting business cards, let's start with Q&A. Let's take the first question. Get your hand out.
So you showed the graphs with the latency where you showed average and 99%. And at the same time, you're dealing with millions of transactions per second. So it would be a little bit more informative, I think, if you could show full distributions for that. Because you could very well have one transaction that takes 10 seconds and the application depends on, the event.
You're talking about full latency distributions?
Yes.
So you're right, and actually Cassandra Stress, which is a tool that that's used for generating those graphs. Actually, that was YCSP, but we also used Cassandra Stress. Recently, I think a week ago, gained the ability to output high dynamic range histograms. So when we do the next benchmark, we will use that, and you will have full histograms, and we will of course show that on our website. Another thing that they added was support for coordinate omission. So I'm not going to go into that, but coordinate omission, I will go into it a little bit, is about measuring the effects of having a garbage collection event stop lots of requests simultaneously, and so the impact on the application is much greater. And when we run our next benchmark, we will use that to show the effect. So
I've just seen these kind of benchmarks all the time, and it sometimes can be very, very misleading because you're not actually measuring benchmarking what you're actually interested in some situations. In terms of, you're missing like 10,000 of those if you have a million per second, right?
Mm-hmm.
So if the distribution is not in your favor and a few of them take very long, it might be something that you need is you have a maximum time that this request will take. Some kind of
so I can't do a lot more than wave my hands, but when we do get to those full distributions, you will see that the difference is even greater between Cassandra and Scylla, and this is mainly because of the GC. With Cassandra, the latency is basically unpredictable, also because you have all of those threads competing with each other, and with Scylla, you have a much simpler architecture, and it's up to us to generate the next benchmark, and you can also try it yourself if you like. It's pretty easy. And our benchmarks are well documented. All of the recipes are there. We document everything.
One comment on that one. On the Cassandra Stress, you actually can define the distribution that you want on every parameter in every column as well. So you can have different distributions inside as well.
What do you mean by that?
So every column can have a different type and a different distribution of the size and the frequency of that. There's a Gaussian.
You can check Gaussian distribution and plenty of others. I can testify, of course, I'm totally biased, but we're an open source vendor who's committed to open source, so most of the time, as the CEO of the company, I try to push to publish more benchmarks, and the engineers scrutinize me if something isn't maybe down accurate to the very bits. So we take a lot of consideration into being fair, and most of the time goes to test Cassandra and tune Cassandra so it be a fair comparison. So
It was not a critique in any way.
Just
I see this very often when I see benchmarks, and I mean, if you're not actually measuring what you're actually interested in, most of the time people actually don't measure what they're actually interested in. So they say, okay, 99% percentile looks like that, so everything's fine, where in reality there are some things that are...
Look at the whole range.
The reality is even more in our favor, but of course it's just hand waving. We will try to provide more data in the next benchmark, so the full latency distribution, including the maximum and all of the percentiles, not just the 99.
This particular one, it's YCSP workload A. We tested the 6 workloads, so from 100% writes to 100% reads, 95 divide and all. This uses 10 million rows, so it could fit in the memory, but we also tested 250 million rows that doesn't fit in the memory, and the distance between Cassandra and Scylla was huge. So, but it was that huge that it looked ridiculous. So I just wanted to publish this one.
Is your scheduler like a loadable module, or is it something that's in user space? How did you say you bypassing the buffer cache, all this stuff? Are you doing like direct I/O? How did you do that?
Okay, so first there are two schedulers. There is the CPU scheduler that just does a regular run to completion. I guess that's not very interesting. The IO, are you talking about the IO scheduler? So yes, so we do AIO and ODirect. So all of our IOs are bypassing the page cache, and it's a simple queue of operations. And there is a blog post on that with lots of good details.
So you implemented that as a library, not as a loadable module?
Yes, it's part of the C-Star project, so it can be used in other projects.
Two questions. One, how do you make money? And two, what's the largest implementation you guys have done? I just want to get an idea, like you talked about up to 15 Cassandra nodes, but like, do you scale to thousands of nodes? Have you done it?
Yeah, so first how we make money, we sell subscriptions, and with a subscription you get the support, you get extended life cycle, so you don't need to be on the upgrade treadmill, and you get our management console. And about the largest deployment, I think the largest right now in production is 30 nodes in 3 data centers. We've tested, I think, 100 nodes, and I think that the 100 node cluster is equivalent to about 1,000 node Cassandra cluster, which is the biggest in the industry. So we scale practically for all, it's practically infinite for all purposes.
So I think you mentioned that you drop in compatible with Cassandra 2.1.6. What about 3.0? Like, when will it be available?
So it's a good question. So we already have a few features from Cassandra 2.2. The user-defined types, I think, are from 2.2. Not exactly sure. We're adding features from 3.0, like materialized views. I showed them on the roadmap. So we are working with that. We will not necessarily implement every single feature from Cassandra. Not all of the Cassandra features are created equal. Some are not really well thought out, but the ones that are useful and are used by users, we will implement. And if you're interested in a specific feature, then you can ask on the user mailing list or on the bug tracker, and or contact us directly. And we are prioritizing features according to customer requests.
What cloud systems and hypervisors have you tried the C-Star project ScyllaDB?
So of course Amazon, but also Google and Azure.
And OpenStack and VMware,
Yeah.
so practically VirtualBox too, because people begin with that.
And Docker.
Because I was always wondering if under the covers when they do their hypervisor stuff, does that mess with your carefully adjusted C-Star world?
So I won't say that I love running Scylla on hypervisors. It does reduce the performance somewhat, but the performance advantage is still huge. And on Amazon, for example, you can request enhanced networking, and with enhanced networking, you get a NIC bypassed. So it bypasses the hypervisor and is available directly to the guest, and that recovers most of the performance. So be sure to ask for enhanced networking, and our installation should recognize it and take advantage of it. And that's it.
Yes.
When you say the releases, almost every month we are releasing it. How within the month you develop and test and release it?
So we are 10 times faster than in development, not just in runtime. So we have a quick team, and we also have a backlog, and we have a lot of automated tests. We have a 4-part or maybe even 5-part series on how we test everything automatically, so our release cycles can be short. No doubt that in the future we will slow down the releases a little bit, but we are still committed to moving quickly. In open source, the motto is release quickly, release often, and we're making good progress in delivering useful features.
Some of the releases, it's a lot of major differences you are bringing in.
Yeah, it's a release train, so not necessarily all of the features take 1 month to implement, but sometimes we begin the implementation way before, like the outer table and outer key space began around January, and we already began to work on materialized view already, but it will become available later.
Yeah. It's a good example. Outer table was actually available in 1.0 under an experimental flag. So the code was implemented, but we haven't completed testing. And in 1.1 we just enabled the code that was available before, after we completed the testing. So it doesn't mean that we implement everything in a month, but we are working very quickly.
Even Thrift support, we have half-baked implementation of Thrift, which was available a year ago. Before the beta, we decided to disable the Thrift support and make sure that we focus on things that a smaller amount of features that are hardened. So knowingly we disabled Thrift support, which is still there. So if you add developer mode flag, then you'll get a partially implemented Thrift. So and right now to finish the Thrift implementation, it's not that long. That's part of it.
We have time for just a couple more questions. Yes.
I know Cassandra does just take a row and dump it out as a JSON for storage. You mentioned that. Same with Mongo. How do you guys store it? Are you guys better at handling incrementing numbers?
Handling at what? Better at what?
Incrementing numbers.
Oh, you mean counters?
Yeah.
So actually we haven't implemented counters yet. That will come later. And actually depending on demand, we understand that the counter features is not one of the better Cassandra features. It's not completely accurate and it doesn't scale very well. So we're not 100% sure that we will implement it soon. It really depends on user request. But right now there is no implementation and not even a half-baked implementation like we have for Thrift.
We're going to do the raffle in a moment. Did everyone have a chance to put a card in?
I did.
All right, let's do the raffle. Let's take a break, do the raffle, and come back to another couple of QA questions. Can I ask you to reach in and just mix up all the cards? All right, now look the other way and reach in. Don't look in. Pull out a card, read it out loud. Well, don't look in. Read it out loud.
Joseph Rubini.
All right, put the card back in. Congratulations, Joseph Rubini. Let's take 1 or 2 more questions until we run out of time. Anyone have a question? Yes.
How much funding do you guys have? Like how much?
Do you want to invest?
No.
I'm not going to answer this question. We are well funded. We have we're a large team, about 25, I think a little more. Don't worry about that.
All right, on that note, thank you all. Avi Kivity, CTO of ScyllaDB. Thank you.